Okay, Michael is for you, Steve.
Okay. Um, First and again, um, welcome back. And just to begin with the most important thing, thank you for coming back. Uh, Francois had suggested that for this time, we could go back to something a little bit closer to a little closer to the origin of our business. And it's well, I hope this will make some sense. This is going to be a little bit of a mixture of conceptual history and everything that you know very, very well. And I'll try to make some simple things very hard. So you'll see why it really is much more subtle and beautiful, thinking of the physics of the problem of light than we sometimes give it credit for being. A way of putting this is that typically when optics is done, it's like at the end of high school, lycée, or at the beginning of physics in like first year of physics, and it's something that you just jump over because it's an application of geometry and lenses and whatever. And the real complication of something as simple as tracing a ray of light gets glossed over. So that's where I wanted to start. Okay? So um, can you see the slides now? You should be seeing the word light.
No, I don't see anything.
Okay. Um, let's do the share. Now?
Correct.
Yes, it's okay now.
Okay. Um, there's really no subtitle here. Uh, the let's get to the basic point that one of the enduring problems facing the development of early modern science was an understanding of the nature of light.
Merde.
You see, just
Euh,
just to make this point clear as an introduction, optics, that is geometric optics, had to a large extent been a classical problem in the application of geometry and was already pretty well understood, at least at the practical level, through the 16th century. You had Roger Bacon in the Opus Maius already describing the functions
ah,
of mirrors.
merde.
Gross test had already worked out some of the
Euh,
basics of the laws of reflection. The phenomenology that you find in Della Porta's Natural Magic is virtually the same thing that you find in the introduction to Galileo's Siderius Nuncius, that the understanding of light as the propagation of rays, or put differently, that light equaling a set of lines that you had traversing space somehow, was well understood in the sense that you could calculate with it. What wasn't understood and what was so deeply debated for the period up to about 1600 was the other side of this, the ontological side. What the hell is light? More to the point, something as simple as where is it coming from? Is as in Al-Kindi, is it coming from the eye to the body that's being observed, or is it something that's coming from the body to the eye, or is it something that's coming from the environment? What is the nature of the emission process? All of this was very, very much uh, up in the air. It wasn't until the middle of the 17th century, specifically with three characters who figure prominently in this. Descartes, who had introduced the idea of a propagating medium, mainly for the transmission of force, that is the ether, or some kind of universal vortex bearing structure that could transmit force and ultimately was the source of what kept the planets moving and kept bodies moving. It was the source of inertia. It was also seen as a medium that could transmit. And no matter what light ultimately would be, there was this universal medium that somehow could support it. Where things got more precise was in the second half of the century, when, in particular, two treatises appeared. One, the one on the left, which is Huygens' treatise on light, and the one on the right, which is the culminating book of Newton's investigations of light. These are as completely different approaches as you could possibly imagine. That is, uh, Huygens took very seriously the idea that there was a universal medium. Never mind what it is, never mind how it does it, but since elementary observations, just sitting on a beach and looking at the waves, shows that you have something that propagates, and that propagates in lines, in the sense that you have a wave that comes in a straight line and is followed by other waves. That becomes an analogy for the way that light, again, whatever it is, can be transmitted through an elastic medium. Newton, on the other hand, took the same approach to light as he did in the optics, in the Principia, that space is not a filled medium. He spent an entire book, one of the three of the Principia, and then returned to it in the General Scholium when he was dissing Descartes in every way he possibly could, that this medium could not possibly be the source of gravitation or the motive principle for the planets, because it didn't obey the proper fluid laws, and ultimately the easiest way of understanding force was impulsive, that you had force being transmitted essentially in impulses, and those were transmitting momentum, and consequently force was actually the rate at which the momentum was being transferred, unlike the way we usually teach it. His concept, therefore, was anything that propagates at distance, especially light, had to be done the same way. That if the world is a vacuum, the guy on the left doesn't hold. It's got to be the one on the right. And to make things consistent, which is hardly something that Huygens was concerned with, that he was treating two fundamentally different things. When he was talking about mechanics in other contexts, it was not a matter of transmission, it was simply the notion of force. Newton, on the other hand, was trying to create a universal law. And so for Newton, light was impulsive. Now, we make the mistake, and this is why I'm going through all of this, of saying that Newton had some concept like the photon. That's garbage. What he had was fits of emission without having the slightest idea what that meant. So these were ways of, in a vacuum, transmitting something that was called, if nothing else, particles of light. So uh, this was a quick one to just put things in context. This is essentially the way that you would think of what Huygens was talking about, that you would have a medium which was being excited, which in time, because of spatial connection, because you had this medium, this ether that had already been postulated by Descartes, connecting everything, what happens in one place has an influence elastically on what's happening in another. Now, all of this, to make this clear, all of this was happening at the same time as the concept of force and the notion of particles versus continuous media were being worked out. And that took another 100 years for elasticity that had already been, that is, strength of materials had already been something Galileo had dealt with, to finally get to the point where you could talk about the dynamics of a continuous medium. But Huygens and those who were looking at gravitation as being something transmitted through a medium, not necessarily this set of vortices, but that there was some universal base above which you had matter and excitation, but that space itself was not empty. As soon as you say that, a wave is the immediate result. There's no other way of looking at it. But because of that, you also have something that Huygens introduced that becomes absolutely central, that a wave is something continuous. And so every point on the wave is an excitation for something that's going to propagate ahead from that point. And that's why I drew this first diagram, that every point along this line is an excitation. And from that, because every point here is connected with every point here and connected with every point here, just like this, when you have something that's oscillating, even if one of these is oscillating and the other isn't, this one on the right will be excited because it's connected to the one on the left. And the thing that connects those is, oddly enough, the same thing that Hooke had talked about in what actually was the first quantitative force law, the one that you all know, that if you stretch a string, the more you stretch it, the greater the reaction force is going to be. That's exactly what you're looking at here, except you're looking at an ensemble of these springs. But without even knowing the nature of the medium, because it was already known that elasticity, as in springs, was something that changed depending on what the medium was made of. But the basic law that the more you extend it, the more of a reaction there is, that was already taken as universal. So the notion that you could have, and now I'll use the word, phased oscillations at a point in time in space meant that every point on that phased wave would be the source of the next level of the oscillation, the next phase. And so you have the concept introduced, which is absolutely fundamental to everything else we're going to talk about, that if you deal with time and not just space, and you got to remember that classical optics had no time. It was just geometry, and so it was just space. But the idea that you could have sources and sinks automatically introduced time, which introduced two things: the phasing of the excitation and the rate at which it could propagate. So what Huygens had done was, in effect, the same thing Newton was trying to do, except Huygens had done it with a continuous medium and so required something to support it, while Newton had gotten the concept of time and propagation, but hadn't gotten a medium with which to make that happen. Now, this is the sort of thing that Newton would have a very difficult time explaining. This happens to be a lamp in a pizzeria that's near home. That this is the lamp, and it happens that it's got a spherical bottom, and so you form a virtual image at the focus, and you also form a reflected image, and this is effectively the same thing as a mirror. So you have a source, and that source propagates outward, and then reflects here exactly as you would have if you had rocks on a beach and the wave front extends out from this, propagates to the edge, and then reflects back. So the basic laws of reflection were all obviously dealt with, and waves could perfectly well explain this sort of optics. What you had problems with was this, uh, that this is a laser, a laser pointer in a glass of water in my kitchen, where you have two things happening here. One is transmission, which changes the angle. So you have Snell's law, which was, again, as a geometrical effect, perfectly well known by the middle of the 17th century. And you also have something that Descartes had already figured out, that you've got internal reflection here, and that this ray is going to come out refracted at a different angle, and this ray transmitted is going to come out at a different angle. And lo and behold, you have the basis of the rainbow. Okay? But you have no idea what light is. All you know is that you have an effect in which the medium changes, excuse me, the direction of propagation. Now, the problem with Huygens was that what was happening here was very difficult to explain. So the real question that was sitting in people's minds and now became central was what happens when light interacts with a medium? Because it was clear that this was some kind of propagation, and that depending on the nature of the medium, things changed. Now, the next is, and I'm skipping the whole of the 18th century because that's a whole other story. With one exception, I just realized I should mention this. There's a wonderful paper from the 1750s in the Philosophical Transactions of Royal Society. I think it's in 1757 by a certain Dr. Simmer about his socks, or in Italian, calzini, that is actually a description that begins with his taking off his socks in the middle of winter when the air is very dry and noticing that there are sparks. In other words, he has wool socks. He's removing them from his sweaty little feet, having removed his boots. And when he pulls them apart, there is a crackling sound and the emission of light. Now, you got to realize that just about everyone who had ever put on a pair of socks in that century would have seen the same thing. But for Simmer, this happened at an absolutely perfect time. And it sounds silly, but this is actually a remarkable paper, one that John Heilbronn highlighted in his history of electricity and magnetism in the 17th and 18th century, that what you have is the first careful empirical description of an electrostatic discharge producing light. Now, again, everyone and their cousin knew that this happened, but this was connecting something with a phenomenon that had been the rage in the middle of the 18th century, namely static electricity. You, of course, know one example of this, which is the emission of light by lightning and the famous experiment, the uh, the guard box experiment and the kite by Franklin that demonstrated that an electrical discharge was the origin of lightning. But the other side of this was the recognition that an electrical discharge produced light. And so the two of those must be connected. What wasn't in what was also obvious was since lightning seems to come down from the clouds, or at any rate propagates, there must be a propagation timescale for the effect. And so the nature of the medium, so now we're getting a little farther. The nature of the medium, the concept of phase, the presence of a uniform medium and distributed sources allows you to think now that light might be somehow connected with electricity and with time. Now, this is the centerpiece of the discussion of waves in the Beckerian lectures uh, by Thomas Young. This is the famous double slit experiment. This is the diagram from his later treatise on light. But this is the first application, distinct application of the concept of phase that was so central to the wave concept. But I just wanted to point out that this happens to be a photograph from a beach in Geneva. Uh, if you take a wave that comes in from this direction and you diffract it through an irregular slit called rocks, you wind up getting exactly the pattern that the double slit experiment showed. Okay? What this demonstrated was, by analogy, a medium that shows phase and waves exactly fit the physical behavior of light. Okay? This is a, although this seems banal, and now it's so much a part of our culture that we don't even think this is all that important. This was absolutely vital because one of the other things you notice, and you know this from experience, is that these alternations of maxima and minima are at different angles, and they also have different intensities. That when you actually look at the pattern on the screen, the individual fronts here are not, that is, as they project onto the screen, are not at the same intensity. And that means there is a principal direction of propagation, and that within the wave, and this was the point that Young stressed in rediscovering Huygens' principle, every point on the wave, here at A and at B, serves as a source for the wave. If you put a slit in, you've interrupted this. And so you've lost the intermediate sources. And what you're seeing then is an isolation of a point on the wave with the whole medium outside of that. So you could think of this as all of space sitting out here and having excitations at just these 2 points, like sparks, and from those you would get the propagation of waves, which would then, and this was his point, interfere with each other because you were driving the medium in different phases at the same time. You could, in fact, get cancellation and you could get addition. But what you had was the propagation forward. Okay? This also explained what could happen if you put an optical medium in the way. And this happens to be an irregular water drop on top of a plastic DVD cover, imaging a light, just a bulb behind it. The formation here is an image which is magnified and intensified, which is exactly what you would expect, from the interferences. And then you get some very strange structures here because of the irregularity of the lens. In other words, this is simply the mapping of an interference pattern. Okay? And so I hope this is clear. This is finally the thing that connects everything together. That once you have the concept of phase, you also have the concept of image formation. That what you're taking is a plane wave, moving it through this and mapping it onto a surface in such a way that the same phases either add, so they're constructively adding by amplitude, not by intensity, because you have the amplitude being the magnitude of the forcing and the phasing being the relative direction of the force, since after all, force is a vectorial quantity. So the timing of those, that is, how the point from here arrives onto the surface compared with the point from the center arriving at the same point, gives you the variation in the intensity on the surface. In other words, you suddenly have an explanation for what had been only geometric optics. And you have the possibility with this of inverting. That is, the image becomes a map of the light going through the lens. So if you know the structure of the lens, you can go from the image back out to the source. Okay? The next thing was recognizing that another phenomenon was, and this is where we get to the astronomical side of things, that again was well known, was a demonstration of the effect of the medium on light. This is just sunset at Viareggio. These images were taken just a few minutes apart. You can already see that there's some structure in the image of the sun, several different layers, and also that it's already flattened. Now, Pascal, in his famous experiment on Puy de Dôme, demonstrating that the pressure goes down as you go up in the atmosphere, had already demonstrated that the atmosphere of the Earth is stratified. Okay? This may seem as if it's coming out of nowhere, but if you know that light is refracted and that the refraction depends on the density of the medium or the properties of the medium, what you're seeing in the sunset is a map of the density structure of the Earth's atmosphere. And more to the point, that the sun turns red as it's setting, as it changes color, is exactly what you see in the rainbow, that in the interaction of light and matter, it depends on wavelength. Whatever the hell that means, it could mean that light, if you were Newtonian, you would say, well, light at one color has a different speed than another. It doesn't matter. The point is that you're probing the medium. Now, I'll jump ahead and say something that has nothing to do with the rest of our discussion, but it's important for those of, for all of us as astronomers, that what you're seeing here is the way you're supposed to really treat an exoplanet in transit in front of a star. Okay? That you can think of a sunset as being the same thing as an eclipse through an atmosphere. And that here, when you have this hard surface, otherwise known as the surface of the sea, what you're really seeing is the atmosphere above it and the transmission through that. So the timing of an eclipse, when you have a planet or star eclipsing another star, depends on the density gradient and depends on the wavelength you're looking at. So you could invert that and look at the eclipse of a planet and in say, seeing it move in front of a star and looking at different wavelengths, you would be able to reconstruct the structure of the atmosphere. Now, that's an aside, but it's a direct application of something as straightforward as this lens. Now, this is the other example um, that this, called a caustic, is simply an ensemble of focal points where the primary focus is here, and all of these just happen to be where you get co-adding in phase waves. But because I used here a thin lens and an almost monochromatic light source, the image here is a unique image. But if you did the same thing, transmitting through something irregular or even ice, you get this. I hope you can see this.
Yes.
This is actually a spectrum. The sun is off to the left at an angle of about 20 degrees. This happens to be, uh, there were some very high cirrus clouds. Uh, this happens to have been late September uh, on the Tuscan coast, but there just happened to have been a cold front that had come through, and these clouds had ice crystals in them. They were at very high altitude, and just at sunset, there was this caustic form that is in colloquial English referred to as a sundog. So in other words, you can get dispersion from either liquid, and that is drops, which is sort of what you're seeing here, or you can get dispersion in different wavelengths. If you go back to this for a moment, if any of you have heard of the green flash, and I think many or all of you will have, that's effectively what you're seeing, that there are different opacity sources in the atmosphere, and the green flash is very much like the red flash. It's when you have a particular ray that isn't absorbed that appears above the horizon during sunset when you have a very sharp edge. So, um, diffraction shows up in a lot of ways in natural settings. I mean, this is just the effect of dust in the air and the scattering of light in a cloud. The thing that's important about this image is that whether you're using particles and trajectories or you're using waves, you'll get the same answer. Here it doesn't matter because you're not looking at something coherent. All you're looking at is either absorption or scattering. And here, the reason this is dark is simply that you're reflecting light off of an aerosol background. Okay, all of the particles in the air. Another version of that is this, which is again, an ensemble of caustics. This happens to have been in the winter. This is Prague a few years ago. And these bright points are simply interference exactly as you would have if you built a kind of hexagonal crystal prismatic structure and you just diffracted the light through it. This is not the same as this. This doesn't depend on coherence. This does. This is an interference effect. This isn't. Okay? I hope that's clear now, because that difference is essential for everything else we're going to talk about. Now, um, this I hope won't scare the hell out of you, but this is this is the history of electromagnetism in a slide. Um, what I wanted to try showing with this is the way different pieces interconnect. And it's easiest to do that in the context of names and phenomena, but it's not as complicated as it looks. What I've written up here are just the principles in the story that Faraday is experimental and introduces the concept of field, this notion fields as the primary thing. The first connection here is Faraday and Maxwell. So let me jump forward. The development between Young and the middle of the 19th century is really the critical period during which astrophysics is also born, in which the modern concept of optics is born, and virtually everything that we now take for granted about optics, telescopes, control of optical systems, all of that begins in this period where waves were taken seriously. That we we still teach them because the most important feature is the concept of coherence. And that's what I'm going to be talking about in a few minutes. But just to start with this first connection, Faraday was the one who introduced the modern concept of a field, which is to say that you have something that extends through space that has no inertia, that isn't an ether in the classical sense of an elastic medium, but that somehow supports propagation of physical effects. This is before you have the notion of a photon, which is a way of breaking that up into coherent pieces. But this original concept that we still teach as electromagnetism is that there is no vacuum. There's a kind of minimal state that we can't know. We simply take it for granted that it's there. And if you change a charge, if you start a motion, if you move a body, that you generate a propagating disturbance in that medium, the speed of which is at this minimal level of there being no sources in the medium, just transmission, becomes the speed of light. If that sounds like a cop out, it is. Uh, that's the other reason that I thought it would be important to start with this conceptual business. Uh, this is a cop out. This is a way of not asking what that is. It's one thing to say that we no longer have the ether. We don't. We no longer need it. But to say we understand what the vacuum is, that's one of the most important questions that remains unanswered. And it doesn't matter whether you're talking about the Higgs field or any other explanation in modern physics. There's this thing called the vacuum that we take as the basic state. What Faraday did and what Maxwell quantified and systematized was to introduce the idea that space itself can propagate a disturbance, that you have a source, you have the propagation, and you have the reaction. And that the propagation that Maxwell found, based on all of the behavior of electrical phenomena that changed in time, matched light. The most important step was in realizing that there was a connection, and now we come back to simmer. The reason I mentioned the socks between the dielectric properties of a medium. In other words, how a medium transmitted an electrical influence and the index of refraction. That glass, for example, is a dielectric, and the way that it retains charge and the way it transmits electric fields is related to the index of refraction. That was the key result that made Maxwell say that what he was dealing with wasn't just an electromagnetic field, but light. That is, he had the magnetic properties of media and the electrical properties, and found that when you put those together, the number that was produced was what had been found already by Romer in the 1670s. That was the speed of light. And so with that, Maxwell achieves three things: systematizing Faraday, introducing a way of dealing with time-dependent fields, and exploiting the physical properties of media other than the vacuum that could then support the transmission of waves, all of which meant that fundamental to Maxwell's concept, there is, to Maxwell's solution, there's a phase and something else, polarization. So everything that had already been worked out in optics was already there, including, going back one tiny little bit here. Um, so going back here, the other thing that was there was what happens if you put a disk in the way, or what happens at an aperture. In other words, if you put something here as an obstacle, you wind up getting a diffraction pattern. And because of that, the shadow isn't just a point, it's an extended structure. And consequently, you could explain virtually all of the interaction between light and matter by using coherent waves. And if you had emission from many sources and they weren't coordinated with each other, you could have incoherent light, which wouldn't be polarized naturally unless you interrupted the light in a way that put a barrier in the way. In other words, if you had reflection or refraction, you could take an ensemble of waves that were uncoordinated, incoherent, and get a signal that had some marginal coherence. Now, hoping that I can get this to work. Okay, well, possibly ignoring the pad and just going on here. Um, this is kind of going to be the next thing I wanted to bring up. Uh, this this was Ricky at Andreev, and two different generations of radio telescopes. Uh, the first application of electromagnetism was, as you know, Hertz's detection of electromagnetic waves, that when you had a periodic spark, it could propagate across a room. And eventually, by the beginning of the 20th century, you had signals being sent from England to Newfoundland by Marconi, and also realizing that you could generate periodic signals. In other words, waves, that there was no difference between what was called AC and electromagnetic waves and light. Okay? So for the moment, I'm going to concentrate on the next application, which is how do you wind up using phase? Um, okay, so uh, this will be just a quick reminder. Uh, the other thing that, after all, makes light worthwhile for us as astronomers is that we build telescopes. Uh, the telescope is just an optical instrument that's capable, because of its finite area, of collecting a certain amount of incoming radiation, however you want to represent that, producing an image from it, and having some kind of a registration device. It really doesn't matter where you put this, but I want to make it clear why there's a justification for two of these instruments. That's not said very well. Look, this is a this particular project, otherwise known as the Hubble Space Telescope, is a 2.4 meter mirror, low Earth orbit, outside the Earth's atmosphere. Um, this is a 6 meter mirror, JWST, the name of which I won't expand because I don't particularly like administrators. Uh, but this is essentially the same thing, except bigger, and that operates in a different wavelength region. But the point is, it's in space. And so, in these two telescopes and telescopes like them that are outside the Earth's atmosphere, the only thing you have to worry about in understanding the formation of an image is the optics of the telescope itself. Okay? That the formation of an image by JWST is exactly the same as the formation for HST or for any satellite that's been placed in orbit or in far orbit, like around one of the Lagrangian points. There is no medium out there other than vacuum. And Maxwell had already demonstrated that the speed of light in a vacuum is finite but uniform. And so when you're talking about the propagation, here it comes, when you talk about the propagation of phase, a plane wave hitting this mirror comes in coherently. And consequently, the image that's formed by this mirror in a process that we're about to do retains that coherence. Okay? So, in the same way that we were forming the image here, or the other example is here, where the lens, where the drop is more regular, and you see that you still get what are called aberrations because they're imperfections from an ideal image. But you can see the concentration in the edge, so you have a finite thickness of the lens. This is why you would never build a refracting telescope and put it in orbit. Okay? Because you don't want an intervening medium. That's why you put the damn thing in space in the first place. But the fact that you have the formation of an image here, which is almost symmetric and almost in focus, is the result of just the shape, and you don't have to worry about the air in this at all. Okay? I hope that I hope this is making sense. I'm about to make a big leap. Let's back off from light and go back to electromagnetics. That One of the things that Hertz was working with were sparks that were at most at the kilohertz range. He was working at very low frequency because the nature of the discharge was such that he couldn't get very short time constants. One of the most important steps that Marconi and Tesla and Heaviside and all of the electricians at the end, as they were called then, at the end of the 19th and the very beginning of the 20th century, affected was the generation of high frequency signals, high frequencies being in the 100 kilohertz range, so 10 to 100. That simply implies that with the speed of light, you're dealing with wavelengths that are of the order of meters or even longer. Okay, so if you're going to simulate optics with electromagnetic waves, which you should be able to do if they are the same thing as light, you're going to need really big instruments. Now, what Marconi and others were doing in building this weird kind of antenna, I mean, I most of us, I think, are old enough to remember when these things were on the roofs of apartment buildings and houses, that you had this thing called an antenna on the roof, and it wasn't something that was a parabolic dish. These were particular lengths that happened to be resonant points for electromagnetic waves along a conductor in the same way that you have air resonating inside a flute. Okay? That these are the same thing as tone holes. And so this system was resonating at specific frequencies. And you can see this is pretty large. I mean, these are many meters long. So this is something that's designed for fairly low frequency. And actually, this is for solar observations. But if you wanted to, these aren't focused. But if you wanted to build something that could simulate what a lens does, except with radio, you've got to go to, say, something like this, which is still in operation at Nancy. It's an enormous parabola. I think you can get an idea of the size of this thing by just looking at the buildings, where light is reflected off of this. This is actually a Newtonian where the Earth is the telescope, okay? Light reflects off of this panel, then goes to this curved surface whose surface can be tilted. These are actually individual panels. And it's then focused into this building where there is a detector. So what you're doing here is building a Newtonian reflecting telescope, except it looks very much like that lamp that I showed you from the pizzeria. That is, this has a lousy image because the area that this covers on the sky is a very extended region. Okay? The next step, if you really want just collecting area, was Arecibo and now is FAST. You just build a huge dish, in this case 300 or 500 meters across, and then it's exactly the same thing as an ordinary telescope. And so I can use this as an illustration. The way this works, and this is a Gregorian, which means that the focal point is not at this point, but it's actually up here, and then there's a secondary image formation. Never mind how this is done. The essential point is this. The plane wave light comes in this way and arrives at different times. The same phase arises along the whole of the wavefront. Okay? So a given direction in the sky is just a wave coming in like this. But that wave arrives and reflects from the periphery before it arrives at the center. Okay? So when that wave returns to the focal point or just on axis, and these waves intersect with that, they have different phases. Okay? The ones that interfere positively form a bright spot in the image, and those that interfere negatively form a dark spot or rings. Now, when we're talking about a radio telescope, what you say is you have the primary beam, which is the primary lobe, this part of the field that is at the first maximum. Remember, the diffraction through a slit is the same as a reflection from a telescope. This is Kirchhoff's result, that a disk and an aperture produce the same effect. It's because of phase, where the phase is completely canceling, where you get the first zero. That gives you what we would call the point spread function of the telescope. The primary beam, if you're a radio astronomer, or just the definition of a point source. It's because light that goes in here is the same phase as here and here and here, but it's out of phase with here. That also, this travels a different distance than this does in both directions. So when they arrive at the focal point, the phase of the superposition depends on the angle from which it comes. And same thing holds here in millimeter. This is Apex, which was the Atacama Pathfinder. It's a millimeter telescope. It's far more precise on its surface than either Arecibo or FAST because you're dealing with millimeter instead of centimeter wavelengths. But the principle is the same. That is, you have a focal point, a collector, or a reflector that then sends the light through the mirror if you're Cassegrain or prime focus. It doesn't matter. Okay? The only difference is what is the phase when they superpose at the focal point. And this is my attempt to sort of explain this in an interferometer. The key is, just to go back to this, you could break this mirror up. If you didn't have the budget, and given the current state of politics, that's always more likely than not, you could like save a little bit and take, yeah, a piece here, and a piece here, and a piece here, and just drop the rest of the mirror. Now, what you would have when these things reflect to the center, or using the segmented mirror, let's imagine you remove this one, and this one, and this one, but you leave this, okay? So you leave the outer ones, but you take the ones that are a little bit inside. You can still form an image. You know that. You can throw a rock in a mirror and yeah, it'll have cracks in it, but you'll still have an image there because some part of the mirror may actually reflect as it already had. What you'll lose is light and you'll lose coherence because you're going to be introducing either scattered light or simply missing parts of the image because there are going to be phases that won't be there. Now, since light is coherent at the level of a single wave, you can take the notion that gives you this as an image formation device and ask, What would happen if we took the light from here and sent it down a pipe and collected it in a central place? And then the light from here and here and here and so on, that instead of collecting all of it in one place, we had a collector here that was coupled to a collector next to it. Okay, to make this precise, this. This is the VLA in its most compact array. The outlier, the most distant telescope is 10 kilometers from the center of the array. There are 27 dishes, and this is eventually going to be upgraded. It's in a Y-shaped configuration sitting on the plains of San Augustine in New Mexico. So it's pretty flat, although when it's really extended, you can see the curvature of the Earth. But the thing that's important is that every telescope in that is the same thing as this. The difference is that each one of those, instead of imaging, is just serving as a collector. The image is instead formed because each one of these sends a signal to this building, and that signal has a time connected with it, consequently, a phase. When we have light coming in from this direction, it hits different parts of the array at different times. So each telescope sees a different phase. When those signals are combined, their relative phase maps back to the sky. Another example is the one that's online now. This is Meerkat, which is part of the square kilometer array, one part of which is in South Africa, the other part is in Australia. In this case, it is a ridiculously large number of individual antennas, radio telescopes, each one of which has a dish and a collector. It's been very specifically designed along the same lines as the GBT, or Green Bank telescope, which is a 100 meter that has a very particular structure that produces no diffraction spikes. Just to mention this, the the images that you always see from old photographs taken from the ground, the stars that look like the Star of Bethlehem all the time, where you have the cross and well, you have rays extending from the center, usually in an orthogonal pattern. That is because of the supports in the focal plane. Their diffraction. The GBT was constructed in such a way as to remove the supports for the detector and the secondary to make sure that you minimize those diffraction spikes, which means that although you're not imaging with this telescope, you can image by moving it across the source. And you don't have to worry about picking up stray light like from here or here. Okay? Those side lobes, that is, the diffracted part of the wave, those are seeing a different part of the sky. So if you have a very narrow beam, which is what you can achieve optically, you're getting mainly the light from the direct ray and then a little bit to the side, but the phase changes very, very quickly. And so you only see the light that's coming straight at you, which means where you're pointing the mirror. If, on the other hand, you put additional supports in the way, they block the light. And so they serve as the equivalent of slits. Again, this is an application of Kirchhoff's idea that a disk and an aperture are really the same thing. Now, This is very straightforward stuff to the not in engineering, but conceptually, to the extent that now this is ALMA, uh, which is the Atacama Millimeter Array, which is of order 60 radio telescopes scattered over the Atacama Desert in a particular site not far from ESO at very high altitude, but still inside the Earth's atmosphere. Okay? But this is the same thing as Meerkat, which is the same thing as the VLA, which ultimately forms an image because this thing rotates as a result of the rotation of the Earth. That's called aperture synthesis. You take the signal that comes from this, which is a single phase pointing, and use the fact that over time, as the source moves from horizon to horizon over the array, each telescope sees a different phase. That's the equivalent of filling in the missing pieces from here. The problem with the VLA and with the Australia array is that you really have very few telescopes. And in the outer portions, they don't, if this is really extended, the beams don't overlap. So the reconstruction of the image isn't as straightforward as it would be if you had a filled dish. But who the hell is going to give you the funding to build a radio telescope that covers 30 kilometers in radius? Like, no one. So you have to be clever. Uh, what might you might have noticed, these aren't regularly spaced. Neither are these. This is very important that as the technology improved and it became possible to cheaply duplicate the design, radio telescopes in arrays went to something that you might think was obvious, but it certainly wasn't. That if you randomly place these, you get better phase coverage. You get better coverage of the sky. That you don't have the equivalent of aliases. Now, the last one is a little harder to explain, but this is the ultimate use of phase. It's called LOFAR, the low frequency array. If it puts things in perspective, these pads, as they're called, which consist of a set of two types of telescopes, one being what are called teepees, they're just wires, okay? But each one of these is connected with a cable to a central source to combine the signals in phase. And then there's another set of antennas right next to it that handle the higher frequencies. Now, you would think that there's something weird about this because it's just flat. This isn't even focusing. So you should be getting light from everywhere, electromagnetic signals from all over the place. The reason you don't is that each one of these, every single antenna has a phase connected to it. And where phase center is located on the sky can be steered by simply changing the relative phasing of every one of the wires feeding from these antennas. I think this is the most advanced concept of coherence that we have in astronomy, that what's called beam shaping allows you to take this array of telescopes, which literally cover tens of kilometers and cover the whole European continent. There are telescopes in Italy, in the Netherlands, in Sweden. Wherever there's a radio telescope right next to it, it's very likely there'll be a LOFAR station. They aren't international yet. I'm sorry, they aren't beyond the European continent, but they could be. And the concept that goes farther is called the Einstein telescope, the Event Horizon telescope, which is an array of 8 radio telescopes scattered around the world that are capable of imaging, instead of on 10-kilometer scales, on 10,000-kilometer scales. And those are the ones that produce the image that's now famous of the center of M87 and the shadow of the supermassive hole. But that's just another extension of the same concept. All of these use one thing, phase, to create the beam. Now, this is what I meant by the formation of a beam. There's a laser being seen through a curtain, a lace curtain, where it's reflected back, and you see the structure that's imposed, the diffraction structure that's imposed by the threads of the curtain. Okay? Now, think of that as the medium, and then imagine that if you wanted to correct for the effect of the medium, you could shine a laser into a ceiling called the upper atmosphere and observe that laser. And since you know that it's a point source, what you would be seeing would be the effect of the atmosphere on the point source. If you can move the mirror in phase, or the optical system, to cancel out the effects. In other words, here you get constructive, and here you get destructive interference. Now imagine that this is fluttering. You're always going to pretty much see the center maximum, but different portions here will have different phase shifts because the medium is moving. And so if you can move to cancel that out, you can recover this point source image. That's called adaptive optics. The only difference between that and what the human eye does is that it's using an optical system to correct in real time the structure of the wavefront. This couldn't have been done 30 years ago, and it was mainly because of the computer control. The existence of techniques for doing that, the technique was actually worked out in the 70s and 80s. Now, I'm going to skip ahead because you've been very long suffering. This is the inverse of adaptive optics. It's called speckle. If you take a laser pointer and you point it at a wall, you'll see that it's not simply a bright point. You'll see a myriad of bright and dark points within that single image. The image will not be a point. It'll look extended, which is because of your eye. You're actually seeing the point spread function of your eye. But because a laser is coherent, you're forming an image of the wall or the mirror that the laser is reflecting from. And so in your eye, when the lens is forcing that image onto the retina, what you're doing is the same thing I showed you with that caustic and the lens that was sitting under the light. That is, what you were seeing is what you're seeing is this. This is your eye, and the light source is up here, and this is what your retina sees. Now, if you imagine that this isn't just your eye, but that the medium here above this has a column of fluctuating gas with different temperatures, in other words, different refractive indices, then this is going to get blurred out. No matter how perfect this is, every moment, this bright point is going to shift around here, And the whole structure, all of these bright points, will shift around. Okay? This is the image that you call speckle. And if you have a fluctuating medium, that's called seeing. In other words, what you are seeing when you look at a star is the map that of the fluctuations of the density and temperature, hence index of refraction, that your instrument will then register. No matter how perfect your optics are, they will never be the same as the theoretical limit that you would have if you got out of the Earth's atmosphere. The very presence of a refracting medium screws it up. But you can do something really clever. You can, as the English phrase goes, if nature hands you lemons, you make lemonade. Uh, you actually make use of those fluctuations. And this is the paper that demonstrated you could do it by Gazzari, Laborie, and Stachnik. You take speckle by taking a ridiculously large number of very short exposures of a source, and then you combine them coherently. And what you can recover is the information that you're losing from having integrated. That is, instead of having this blob, you can recover some, not all, but some of the phase information. And this was the way that it worked. This is the way that it worked. This is actually the system on the South African Large Telescope, or SALT, that you take individual images at kilohertz rates that are so fast that they freeze the structure of that miserable lens of the atmosphere. And then you do the inverse of using each one of them to remove the shift in the phase. The technical term for this is a Fourier transform. You assume that the signal is composed of fluctuations with a broad range of frequencies, and you go backwards. So you can recover the same way as adaptive optics, which is the correction of the image instead of using the lousy image to recover. Okay? They're two sides of the same coin. One is active control and the other is recovered information, but they're very similar. So the concept of phase and wave deals with virtually everything. The aperture wavelength relation, that is, that the critical factor is the wavelength of the light compared with the aperture that you're passing through. That's what determines where that first maximum is. So that's the spatial resolution. That covers an awful lot of ground, but it still doesn't give us the other side of it, which is that understanding the interaction between light and matter is more than looking at phase, because ultimately that interaction is going to be point-like at the level of atoms. It's not a continuous medium down there, and involving energy and pulses of energy. In other words, this is where you get the necessity for dealing with photons. Photons are principally ways of treating the direct interaction of electromagnetic fields with the medium. Uh, so in, for example, oh, where's a good one? Okay. in this one. These are two different rainbows. Um, they're actually the same phenomenon, but with the source change that the one on the top was taken well before sunset, and the one on the bottom happened to be with the sun like 2 degrees above the horizon. In this one, the sun was like, sorry, in the top one, the sun was about 10 degrees above the horizon. So this one contains the full spectrum. This one has the total blue end missing. That if you actually look at the structure, this is reflecting back through the aerosol that produced it, only very low frequency light, that is red and infrared. Now, why I'm mentioning this is to understand this part of the behavior of light requires the concept of the photon. You can't just do this with waves. Waves will give you the geometrical result. They'll explain why you have, because of the index of refraction, different portions of the wave coming out at different angles, depending on the frequency. It'll also clearly explain why you have a dark band, the Alexander band, between the two images of the light that's coming in, that is between the prisms or the prismatic dispersions. And it'll also explain why the outer band outer bow is inverted in color order from the inner bow. That's exactly what you saw in the light passing through the glass. But what it won't explain is the relative intensity across this. It won't explain the details of the spectrum, and most of all, in both of these cases, it can't give you a sufficient insight into what's going on at the microscopic level. You can talk about this at phenomenological levels. You can put in an index of refraction. You can put in absorption, just as you measure them in the lab, but you don't know physically why it's that way. And this is the other example. Um, if it helps, the top rainbow was looking east, and this at exactly the same time was looking west. I haven't screwed around with the colors here. That really is as yellow-white as it looks. That's what happens when you have transmission through uh, an aerosol medium. That's not that different from this. This is a very heavy fog early in the morning. Um, this is in the late afternoon with not a very heavy fog, but a sufficient amount of water vapor in the atmosphere that you're getting scattering and very particular colors. That is, you're losing almost all of the blue here, and you haven't yet gotten to being dominated by the red. It also happens that it was just after a thunderstorm, but that is very close to this, except the composition of the medium was different between the two. Also, I like the waves here. You can see phase on phase. Okay, never mind. But the reason I'm pointing these out in light of this rainbow is if you're going to understand why that color distribution is the way it is, you have to use the photon. You have to know something about the way it interacts with the energy levels of the material in the medium through which it's being transmitted. That's both a scattering problem and the problem of an induced emission. And that is the point that becomes modern quantum mechanics. Okay? So going back to the map of conceptual history, Planck enters in here with Einstein in saying that, well, when you want phase, phase is the photon. That you can think of the transmission through an electromagnetic field as having momentum being transferred in this wave. And that was already worked out in this interval between Maxwell, Lorentz, and Poynting and Helmholtz, the basic idea that you were transmitting energy. But Einstein went one step farther using Planck's notion of pulses of energy. He said you have coherent fits of emission in that field. Never mind where the field is. Never mind how you create a photon. You say an emission process comes from a transition between energy states, that's the same thing as what Faraday and Maxwell would have called an excitation. And that takes place at a particular energy, the energy and the frequency being related, hence using Planck. And that once that concept is there, linking with Poynting, you have the transfer of energy and momentum. And you don't need a medium to do this. The field itself does it. What that means, don't ask. Okay? That all it says is you have sources in matter, you have sinks in matter, and then you have transmission in vacuum. Doesn't require a medium to do it. But the photon propagating through vacuum or the photon as a pulse has phase because of the arrival. If photons arrive from a single source at the same time, they coherently add. If they arrive at different times, they arrive with phase shifts. And so you have directly the connection with interferometry and directly the connection with the wave concept. Coherence is the same thing as phase. And because the photons are the result of an electromagnetic field, they are also polarized. But if you have an ensemble of them, that is, many arriving at different times, then you lose that coherence. And the photons of so-called natural light, a miserable term, or thermal, even more miserable a term, is just incoherent. But it doesn't mean that it can't be made coherent if you put an optical device in the way that isn't, here it comes, that isn't isotropic. You see, when we were looking at the waves on the beach, so going back to where everything here started, okay, here, these are polarized. That is, this wave is polarized in the vertical direction. That's the oscillation. It's propagating perpendicular to the front, but the oscillation is confined along the front. Okay? Now, think of this in 3 dimensions. Then it becomes a little more complicated. But if you have an electric field that's oscillating like this, then that if it's at one phase and then another phase and another phase and another phase, and this is perfectly coherent, then then the wave will be polarized. And if you have multiple waves, again, this is in 3 dimensions, that are superposed on each other, they're not polarized. But if you put a medium in the way like that, okay, then you're going to pass the waves in one polarization state and not in another. And so you can recover polarization by taking an anisotropic medium, like a slit, and rotating it. And if there is an intrinsic polarization at all, that's the way you'll recover it, which means you use an analyzer. And that's the very last thing we have to talk about with light, because the other thing that is that's there besides phase is polarization. That, I'll come back to that in just a moment. That if the light is otherwise unpolarized and you put a polarizer in front of it, what you'll get is polarized light. And you can find the direction of that polarization by putting in another polarizer. Okay? If the light itself is intrinsically polarized, then you don't need this. You can just put in the analyzer and then look at where in a given angle you get the maximum. There are other tricks that are involved here, but the essential point is that when you transmit light through a non-uniform medium, through an anisotropic medium, in other words, one that has a favored direction of some kind, it becomes polarized. The same thing is the so-called circular polarization signal, as in right or left circular, if you have a medium that's doing that in space. Okay, so instead of it being just one direction, as you propagate, you get a twist. Okay, then you're introducing phase shifts along the wavefront. And the coherence will show up as a rotating field, a rotating amplitude. The way, what that indicates is you have an anisotropic medium, but it has a so-called helicity or handedness. You all know this as the way that you find the structure of DNA and Pasteur's observation that light through organic medium is circularly polarized. So, last point, that this is just a way of explaining what happens in going through the atmosphere. That you have the light coming in that's in a particular direction. It goes through crap called the atmosphere. There are regions that are hotter and cooler, regions that are denser and less dense, regions that are stationary or buoyant, and resulting in deviations of the incoming propagation direction of the light. When you're combining those at the focal point of a telescope, it means that you have that coming in and that going out. And the reason it looks like that is because of this block. That was the speckle idea, that you can go backwards from this to this if you know what this is doing. That's adaptive optics. Okay? It's simply, but it's the difficulty is an engineering one. The simplicity of the concept, I hope, is clear from this, that the longer the path length and the more fluctuations you have, the broader this will be. The closer it is to your focal point, the closer it is to your instrument, the worse it is, because you get shifts in the centroid as well as shifts in the maximum. Okay, so the last thing is something that I hope will be sufficiently amusing. This is the culmination of taking a diffraction grating, an imaging system, otherwise called a camera, and something that simulates Simmer's socks. In other words, building a slitless spectrograph and putting it in front of a discharge in a Van de Graaff generator. So if you look on the lower part, you'll see why the photon concept is so important. This, this is the discharge. So as I said before, the motion of charge And here the interaction between charges and matter is creating photons. Those photons are being dispersed by an optical element that's placed between the spark and the camera. Okay? So what this is showing is the emission bands from the atmosphere, which is the other part of light. This is the incoherent part. This is thermal emission in bands, in this case, oxygen. There's also hydrogen and water vapor, and this line in particular is oxygen, and then these are nitrogen bands. All of those are the result of the passage of a current between these two charges. So this sort of summarizes everything about the connection between light and charge. But I hope this hasn't been, if you'll pardon the pun, too incoherent. It's just that there are really only a very few concepts that are needed, that wave fronts are the same thing as light rays. Wave fronts are fronts of constant phase. Constant phase is the same thing as a photon, as a coherence, and an optical system images because it has a finite angle of acceptance of rays from different directions that, when combined, have different phase shifts. The last point being that coherent light adds in amplitude because it knows phase. Incoherent light adds in intensity because it doesn't. And that has to do with the integration times. If you integrate fast enough, as in speckle, and that I haven't shown this wasn't integrating quickly enough. This isn't speckle, this is just fluctuation. If I had imaged a factor of 10 faster, then you would have seen this itself breaking up in the image because of the transmission of the light between the spark and the camera. But if you image sufficiently quickly, you can recover the coherence. And the coherence can be reconstructed by taking multiple instruments and simultaneously observing the same source. And that's the interferometer. If the Earth rotates and carries the interferometer around so it sees different portions of the sky, basically like that, then you can actually map. And that's called aperture synthesis. The first example, the wave, goes back to the earliest concept. It's in fact the one surviving concept in everything I've talked about. And it actually was the earliest one. The notion of a field is directly the result of waves. The notion of geometric optics being linked to imaging through Hamilton and the concept of rays of light is a direct result of this notion of phase and coherence. And all optical systems can be understood this way. That is, all the ones that we use. So you've been awfully patient. I'll stop here and hope that those of you who are still alive and sentient might might actually have some questions, and that I haven't been too obscure.
Um,
Oh, um, I had to. Um, this was many years ago when I was working in Barcelona with a colleague on Novi, and this is a puppeteer who I think created the best image for a last slide to thank an audience that I know.
Steve, please, could you
Please.
recall the definition of momentum? It was in your conceptual picture with all the links between
Mhm.
the different concepts.
Momentum, in the case of a photon, the momentum is just a scaled version of the energy that um, it's the it depends on there being a characteristic speed for the propagation of an impulse. But when I was talking about it in terms of Newton, his concept of momentum is literally impulse. It's what we would now write as mass times velocity, but that's actually connected with the action of a force, that it produces a change in an impulse, or a change in impulse is the same thing as a force. So that Newton didn't use the concept of energy or of uh, the transmission of energy in time, which is what we mean when we're talking about the photon transmitting energy or a wave transmitting. We don't mean that a linear wave transmits momentum. It's a nonlinear effect. It's when you have something that behaves like a particle, which is a lousy way of saying this. If you've got a duck and it's hit by a wave, and the duck has been appropriately drugged so that it doesn't do anything but bob up and down, that wave is going to cause the duck to oscillate, and that oscillation is going to transmit a wave in the medium. Okay? The duck, on the other hand, will only move up and down, not in the direction of the wave. Clear? That's not momentum transfer. That's energy transfer. It's flux. It's the flux of momentum. Now, if that wave is large, has an amplitude that's large enough and a wavelength that's large enough, then something happens. The natural frequency of the duck starts to interfere with the passage of the next wave. And so the little bugger goes out of phase with the wave and finds itself on a slope. And it actually can be pushed forward. And you know this because when you're in the deep ocean or far from the beach and you have waves going by you, you can lie on your back and just oscillate. But as they get near the beach and they steepen because of the effect of shallower water, the wave rises, you wind up being out of phase with the wave and perhaps on the slope of the wave. And so you get pushed forward or backward. Okay? That's
Mm.
momentum transfer. That's what you get with photons.
Okay, thank you.
Now, the original, the demonstration that you actually could, and it's a mathematical demonstration, that you could get the transfer of momentum was originally thought to be what Poynting demonstrated. And some of you may know that the controversy from the end of the 19th century, we're also very fond of confusing children with this. It's called a radiometer, where you have a bulb that's evacuated and little veins inside the bulb, and you shine light into it and it rotates, even though you're not touching it. You know what I'm talking about?
Mm, mm.
Okay. Here, I'll do it this way.
It was
Hey,
Steven.
Steve. Hey, Steve, it's like a big light bulb with petals that are black and white, and it
Okay.
rotates when light shines on it,
Right.
right?
It looks like this. Okay? Can you all see this? I hope.
Yes, I saw one.
Unfortunately, this when I really need it, the pad isn't working. But um, this is the okay. So you have as as described, you have white and black and white and black, and you shine light into it, and lo and behold, this starts to turn. Except, and so this was taken as the demonstration of radiation pressure. Okay, that the light was reflecting from the bright side, and so you were giving it a kick. The only problem was it went in the wrong direction. And it was a wonderful controversy that lasted for almost a decade and was finally resolved in the simplest way that the dark side was getting hotter because it was absorbing, and so you were getting a kick when the atoms in the not exactly evacuated bulb hit it. So it had nothing to do with radiation pressure. It had to do with the kinetic theory of very low density gases. Why I mention that is that if you understand the concept of the photon, you realize that this is what happens in scattering and absorption. That if the photon is absorbed by an atom or scattered by an atom, it gives the atom a kick. That is radiation pressure. It's the transfer of momentum in the photon to matter. And this is what drives the outflow from stars. This is what actually is responsible for virtually all of the mass loss that happens in stellar evolution beyond the main sequence. So, sort of the ultimate connection that you actually get hydrodynamics being driven by the quantum mechanical interaction of light and matter in a gravitational field. And that's if the object is luminous enough. But the radiometer was originally thought to be the demonstration of what is now called the Poynting flux, which depends on the intensity of the radiation. So the other example is actually an effect that's responsible for the zodiacal light that, and also for producing the tails of comets, that the dust tail is produced in part by solar radiation, radiation pressure on individual grains. And the same thing with the accumulation of dust grains that are orbiting the sun, something called the Poynting Robertson effect, that if you have scattering from a moving mirror, you get actually more impulse in the scattering in the forward direction. You actually get a braking than you would get if you had scattering from a stationary particle. And so it slows particles down if they're orbiting the sun, and so they fall in toward the sun. But that comes in a different context. It's just all of that is related to this notion of momentum transfer, that the momentum is not the same as the energy, and that the key for understanding the key for understanding the photon concept is that it can actually transfer momentum.
Okay. Any other question for Steve? No, so perhaps we can stop there. It is good for our brains. Full.
Okay.
I will send you, of course, the recording tomorrow. And perhaps I can send you um, um, the wave in text. Perhaps it will be easier for some of you.
Francois, if it's useful, I can also make the slides available.
Yes, of course. You can
It's rather large, so we'll have to work out some Dropbox way of transferring it. But if we can
okay.
come up with a way of putting that as a link, this might be useful for people.
Okay, we'll see that tomorrow. Okay, so next time we shall have a new subject. Perhaps we can come back on the spectroscopic development of nova, if Steve agrees.
Sure.
Yeah,
If people
with
are interested in this, yes.
especially one point is the evolution toward higher velocities
Hmm.
during the seek phase of Norway. I think it is a point to develop, but also other point, and perhaps it will
You're
be
getting
the
to one of my
occasion for
prejudices, you
Steve
know.
to present some results on Nova CAS 2021 in nebular phase. And in fact, the nova is not so frozen than that.
So we're just finishing some stuff on this, but the other thing is it's actually an application of many of the things we were talking about today. So okay. And of course, if there are any questions or comments or criticisms, please you know how to get in touch with me. You know my email. I will be very happy to hear from you.
If
Okay.
if
Thank you
possible,
very much,
I
Steve,
would.
again,
Uh,
and thank you for your participation, guys and girls.
Thank you very much, Steve. Thank you very much, François.
See you later.
See you. Bye.
Have a good weekend.
Yes, thank you very much. Bye.
Thank you.
Bye.
Bye.
Thank you, Francois.
Thank you very much, Steve.
I've got to
I keep the
calm the
touch
dog
and
down. Okay.
okay.
Good night.
Bye bye.